So our first speaker this afternoon is Professor Wendelin Werner. He is the recipient of the 2006 Fields Medal. And his topic today was about when randomly chosen objects surprise us. So I'm personally very interested to find out more about that. And thereafter, we'll have the Q&A as usual. It will be moderated by Professor Philip Harms over here. Without further ado, Professor, please.
Thank you, everyone. I hope the microphone is on and you can hear me. Yeah, okay, now it is. It is always a big responsibility for us scientists who have been just working on our science and then have to speak in front of an audience of lots of young brains about who are looking for advice and we don't feel necessarily that qualified to provide advice about, especially for you who are have to shape the world of tomorrow, whereas the world I knew and I grew up with has changed dramatically in these last decades. So what I learned might not be applicable anymore. So it's always a question about what am I going to, what are the main messages that I'm going to want to convey. And the other thing is, I understand probably the first of the couple of mathematicians that you will hear in this GYSS here. And there are two things. The first one is that somehow the bar is set quite low for mathematicians to, the expectations are not that great in terms of what are, we're going to hear a talk by mathematicians. So unless you are a mathematician yourself, you say, okay, well, probably we're not going to understand anything, but it will be interesting to see a curious beast. To some extent, of course, there is a problem because it's very difficult for us to, talk to you about what we actually do, the content of the math that we try to think about. So the usual way is just to talk about something else, about, when is it that we had an idea instead of talking about the idea itself, or explaining that we are somehow different, that we function maybe in a slightly different way than our friends in the other sciences where funding and groups thing is more essential, whereas we tend to say, well, what really we want is time to think and not many people around. Which is not exactly necessarily, the usual thing you tell to funding bodies. And but today I'll just try a different challenge, and the different challenge is really to talk to you about actual mathematics. So instead of making the usual, somewhat usual for me, thing about how mathematics storytelling, I'll try to just give you a few examples of instances where when you choose a mathematical object, so we'll discuss three examples, numbers, functions, or topographic shapes at random, the outcome of what you choose, what you get, typically will be a type of object that might actually be very new for you and very unexpected. And I hope this might stimulate your imagination on different direction depending on your background. And I'll come back to that in a moment. The other thing is that you probably remember, or maybe not because you are too young, that before computers and Beamer PowerPoint presentation became the norm, lecture halls used to have blackboards or whiteboards, then turned into whiteboards, and that we mathematicians used to love that because blackboards, that looks like more adapted to mathematics. And there's actually a good reason for which we tend to still not be very fond of PowerPoint presentation, which is that the mathematics is just something that goes on in our own brain, and having things structured presented on a beamer presentation a certain way with certain colors and certain implications and visual thing like that removes to each of your brains the ability to put it in the right, organize it in the right way, and that's one aspect. And the other aspect is, of course, that we can't process more than one mathematical thought at a time. And when there's too much information on a PowerPoint slide, we just can't process it. So I will, for some time we were stuck with PowerPoint presentation because that was the only option. But now we have these nice tablets, and we can use blackboards, again, on PowerPoint presentations, even though it requires a bit of exercise. And just a little comment is also that many mathematicians, and that's what I do, don't like the commercial software that is provided, and like open source things, and work on Linux. And the best available software for presentation that I'm going to use for you, for us mathematicians, has actually been written by a very good, strong, one of the best mathematicians in the earth, called Denis Auroux, who's a professor in symplectic geometry at MIT. And he said, okay, well, I don't like what is available, so I write my own software, and that's what he did. And that's now we can use it. So that's cool. All right. All right. So the other thing is I'm very bad at keeping time under control. I remember that when I arrived at Zurich, which, as you know, is very rigid with time, I somehow traumatized students when I told them that my grad course in Paris that I used to have organized had the following schedule on Fridays. We start at 9. Okay, if we need a lunch break, tell me about it. And if you need a tea at 4 p.m., we can also make a break, and we stop whenever we feel we are too tired. So of course now, conveying 3 ideas into 30 minutes is a bit of a challenge for me, but I'll try to do my best. So the first little story I want to tell you about is just the simplest one that already got many mathematicians confused by around the beginning of the 20th century, or you might know that was the time, or like 1920 or 1930, where logic had all these big questions about what is provable, what is not provable, the axiom of choice. And in parallel, you had all these quantum mechanics questions about what is real, what is not real, what can one observe, what can one not observe, and so on. And in parallel to that, and that really was paralleling that, there was this question revolving about what it means to choose a number at random between 0 and 1, right? Choosing, so the mathematical word has to do with the Lebesgue measure type stories, but that's something that is very, at least very simple to understand for everyone. You have an interval of like 1, and you just pick a point in the interval uniformly at random. So typically it could be, you choose a time completely at random, and then you assume that you're able to measure, time at infinite precisions. That's what it means. So you know all the digits of, that are involved in choosing that time. So typically, well, you write this number in digits, and it will start, so it's between 0 and 1. It will start with like 7, 9, 8, I don't know. Okay, that's not a good idea because I started on the left, so something like that. Right, so it's a sequence of digits like this. And one of the first, so it's pretty clear that the choice of the first digit will be depending if you are in the first tenth interval on the left, and the second tenth, the third tenth, and so on. The choice of the second digit will depend if you are, say, for instance, here you are between, 1, 2, 3, like this. So you're somewhere here between the 0.2 and 0.3. So now you have discovered this, you're here. And now you're going to divide this into 10 subintervals and choose in which one you are. And that will decide what your second digit is and so on. Right, so you're subdividing, the information about where this randomly chosen point is, subsequently. So in some sense, it's clear that choosing a number between 0 and 1 at random is like choosing a sequence of digits uniformly at random. So the first one, you choose the first digit among the 10 options, and then the second digit among the 10 options, and you do that uniformly at random for all the digits. And there's a very, one of the first results you hear about probability theory, which is called the law of large numbers, tell you that when you do that, you have the sequence of numbers. Morally speaking, the average number of times at which you find digit 1 is going to be 1 over 10. Right? So if you look at the first million of digits, the average number of times you found a 1 in that outcome will be getting closer and closer to 1/10 when the million goes to infinity. That's the law of large numbers. So a typically chosen number will have the property that the average numbers of 1s is going to be 1/10, the average number of 0s is going to be 1/10, and that's true for every digit. So any randomly chosen number will have that property. Now, of course, there are special numbers that don't have that property. 0.5, 00000 doesn't have that property, but this one will not be chosen at random because it's a very special number. Now, do you know many numbers that have this property that the average number of digits of zeros, or 1, or 2s, is always 1/10? So you say, yeah, I know that. I know one is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4. You continue like that, then clear you force it to have an average number of digits to be 1/10 for each of the digits. Now, why do we use these digits, 10 digits? Because we have 10 fingers. That's how we learned how to count. So you could, instead of subdividing by 10 at each step, you could sort of decide to subdivide by 2 and write your numbers in binary form, meaning that this same point, which was here, at first step is on the left, so starts with a 0. Second step, it's on the right, so you subdivide by 2, it's a 1. Third step, it's on the left, so it's a 0, and so on. Right? So instead of replacing 10 by 2, you write your same number in binary form, and then it's a sequence of 0 and 1s that you have. And again, the average number of 0s should be 1/2, the average number of 1s should be 1/2 in your expansion. So that means that if I choose a number at random in the interval 0, 1, it will have the following property. For whatever choice of number of fingers you're using, that we like to call a basis, say if you have B possible options, so you write in basis B, so here this is basis 2, or this was basis 10, the average number of times at which digit A shows up is going to be 1 over B, right? So in binary form, you have, in average, half of the digits will be 0, half of the digits will be 1, and in basis 10, 1/10 of, but this has to be true for every basis. Now the question, can you give me an example of a number that has that property? So you think, yeah, let's, weird numbers like pi or e, they should have that property. And then I'm going to tell you, yes, probably it's true, but show me that it's true. That if you take pi, in any in any basis, pi will have that property. And then you'll scratch your head and say, well, I still think it's true that pi has this property, but I won't be able to show it to you, prove it to you, because it looks very difficult. I need to think hard about it. So, to make a long story short, there are just a couple of numbers for which mathematicians have been able to prove that they have that property. Because all the numbers that you know of, right, these could be pi, e, integral from 0, 1 of something, or some formulas, they are very special numbers. They are numbers that have have been produced not at random at all. And to prove that these numbers have that property, it's like very complicated. So that's the first instance where a number chosen at random has a certain property. But if I tell you, produce me one example of numbers that had that property that almost all numbers have, you won't be able to find it. Right? So this is sort of the first simple example of the fact that, yeah, the objects we know, the numbers we know that we gave a name to, pi or even a formula, right, integral between 0 and 1 of this and that, they are all very special, precisely because they had a number, they had a name, or we could, write them, and that makes them very different what a typical number is. Right? So something chosen typically at random will not necessarily be, the objects you have encountered before. Now, my second example has to do with random functions. So now we all learn, the first things we learn at school in mathematics, not first thing, but advanced mathematics is stories about functions. You have this like that, and you are looking at something like that, t, and here you have f of t or something like that. That's to each time t, you associate f of t, and this f can be continuous, right? So it's like an evolution in time which doesn't have jumps. And usually we draw it like that. That's the way it's, what a typical function looks like. But now the question is, okay, choose one continuous function among all possible continuous functions at random. What does it look like? Well, again, I have to cut a very long story short. But the long story, the story is the following. What you do is choosing a function at random. One way to start with is to do what we like to call a simple random walk, which is at each step, you choose whether to go up or down with probability 1/2. Right? That way you just go up, down, up, and so on. But then you want this function to to be you don't want it to go up and down by during time interval 1. You want to get to some natural limit, and the natural limit is this object that we get here, which is what we like to call Brownian motion. All right, so that's Brownian motion, and there are a number of ways to justify the fact that, in some sense, this is the natural way, one natural way to choose at random a continuous function. And you probably have seen these type of functions before. If you look at say how you call that, stock market evolution, you see these very irregular type things which still look like they are continuous functions. And my moderator here knows much more than I do about financial mathematics. Anyway, so this is like what we like to think about being a randomly chosen function. This is, and it requires some mathematical work, at the level of grad school, to explain that this object actually exists, that the Brownian motion is indeed a randomly chosen continuous function, that it is continuous, and that it has, and to be able to study it and work with it. Now, what I want to tell you now is that this randomly chosen continuous function is a type of continuous function that you've never seen before, probably, if you are, unless you are, mathematicians who like, strange mathematical beasts. So the first remark is that the Brownian motion this curve here that is drawn is oscillating a lot at every infinitesimal level, right? So it's sort of this, goes up and down a bit all the time, infinitesimally, so at each scale level you have this thing, it goes up and down. So in particular, it means that this blue curve here will have infinite length. So if you really try to follow a Brownian motion with your pen, starting from left to right, following this blue curve, well, unless you're using a tablet, like I do, you will run out of ink after time 0. Because immediately you go up and down so much at infinitesimal level that the length of what you're doing is infinite. Right? So this is not at all a type of function that you are used to, like a smooth function, which has a derivative, right? When you know the length is just the integral of the derivative or according to time and things like that. This is not at all this type of object you are used to. This is going to be a function that has differential nowhere, so it will be very, very irregular, has this infinite length. All right? So that's just one example of something that you get. We choose a randomly chosen function. Well, it's a type of function that you have never seen before and that you didn't really think about that. This is a generic case that these functions, usually the way is, the simple functions are the ones we know. They are the ones which are differentiable, and the ones which have, infinite length, these are the pathological things that only mathematicians care about. But actually, no, these are the, generic ones. Now, I'm going to tell you a story which is now more advanced, but it's sort of more that I like to tell in my grads story, and I'm going to do it with with my drawing. So now what I want you to think about is that this line, this green line, is the real line where the Brownian motion is moving. So it moves from left to right like this, right, horizontally. And what we're going to do is that on the top, this Brownian motion is going to carry a pack of sand, which has a hole punctured. So it leaves some trace behind it. And somehow, after some time, it will have left a sand pile behind it. And the height of the sand pile at each point will sort of reflect how much time the Brownian motion spent at that point. So let me, before doing the example for the Brownian motion, imagine that you do the same thing. You start at 0, and you go to the right with your punctured sand pile. Well, after a certain time, you're here. You go to the right at constant speed. So what will happen is that the sand pile will look like that. Right behind you, it has a certain height wherever you've been. And because you went at constant speed, this height is constant. And then here is 0, 0. Is that clear? And you continue moving to the right, and then a bit later, the sand pile will look like that. That's what happens if you move to the right at constant speed. So you see that here the sand pile necessarily has the property that the sand pile profile is not continuous because it makes a jump here. On the other hand, the Brownian motion is moving, like crazy, like that. And what happens is that at every time, if you look at the sand pile that you have obtained, it will be a nice continuous shape. Right? So what you get is that the Brownian motion, if it moves on top of the sand pile it has constructed in the past, is going to create always, a continuous sand pile, which we like to call local time for probabilists. And then again, there's the question, do you know any function that has this property that at any time the sand pile in construct is actually without, discontinuity? And the answer is, I don't think you'll be able to produce me a single one that has that property. This is just what Brownian motion is doing. A typically chosen function will have that property, and it will be very difficult for you to find anyone with that particular property. A further example is that this gives you an example of something very strange. And the very strange thing is, well, it's not that strange because we all did that as kids. You know, we're given a piece of pen and you have to color a sheet of paper. And usually, you know, you do that as a small kid and you color, you know, shapes in blue or something, or I don't know, some dragons, and you know, you have to color with your piece of pen a surface, and you do it like that, and okay, and then after some point you realize it's not the most interesting activity and you want to actually learn to write or something like that, but they just tricked you to learn how to hold a pen or something like that. But here now the job is the following. The pen I gave you is infinitesimal, right? It doesn't have any thickness. And I asked you to color a piece of surface in a finite time using this pen, which actually only visits points and doesn't have any thickness. So what I'm asking you is find a curve that moves around in two-dimensional space and that visits all the points, right? A space-filling curve. And this example here is actually one, because this thing is moving around like that, filling, you know, creating the sand pile after some. And after some time, the sand pile will reach, at that point here, will reach that level. And so that means that at some point, the point at which the sand pile did reach that level, this Brownian motion, which was growing on top of the sand pile, past sand pile, was visiting that point. That's true for every point. So this way, you have constructed a way, function that actually fills in the entire plane. Exactly, again, an example of something you wouldn't expect, you know, to be possible at all, to find just one of these space-filling curves. So a function chosen uniformly at random, the Brownian motion, and if you add this little tweak with the sand pile thing, provides for you a way to fill in space with the curve. All right. So now what I want to say a bit further is that Brownian motion is not only interesting for people interested in stock market, it's actually a fundamental building block to understand a number of things that have related to most elementary physics. You probably all know Newton's law has to do with 1 over r squared interactions, the potential 1 over r, and this is very closely related to harmonic functions, the Laplacian, and Brownian motion is behind the scenes as well. So in particular, Brownian motion is interesting not only as this one-dimensional curve like that, but as an object that moves around in space. Right? So this is the random trajectory, if you want, of something that you could view as a little fly that has no memory and is sort of oscillating around. It has infinite speed, but of course, because it changes its mind all the time, it has no sense of where it goes, no direction, but it sort of moves around in an isotropic way, completely erratic. Right? This is this Brownian motion, dimension 2 or 3, that you can view like this. What happens is that if the 3 coordinates of a 3-dimensional Brownian motion would be actually 3 independent 1-dimensional Brownian motion, which were the previous curve that we did draw when you look at it with respect to time. So what sort of trajectory is a 2-dimensional Brownian motion? Well, you just do a little simulation, and this is what a trajectory of a 2-dimensional Brownian motion looks like. So again, this is sort of a very strange beast, because in some sense you should view it as having infinite energy, right? It's sort of it's not moving around like crazy, but because it's not organized enough, it still remains around and moves continuously around you, but it has this infinite energy in it that it tries to organize. Now, if you look at the trajectory of a 2-dimensional Brownian motion, it will have properties that you would never have expected a continuous curve could have. So that would be, again, something essential. So just to give you an example, during time, on the time interval between 0 and 1, there will be a point somewhere. Of course, it's a very special point on the trajectory. that this Brownian motion will have visited infinitely many times. So during the finite time interval 0, 1, there will be a point that the Brownian motion will have visited infinitely often. And these points will be actually, spread all over the trajectory. So, and again, if I try to ask you, produce me a curve, a two-dimensional curve with that property, you'll be very, very in deep trouble. So here we are now in a situation where, and of course I can't elaborate more on that, but these type of very strange properties of these Brownian paths turn out to be very closely related to fundamental issues having to do with fundamental physics, because the Brownian motion is behind the scene of the interaction forces and so on in physics. And so what started to look as exotic thing and why are you interested in these and those properties of Brownian paths, actually they are very important elements to understand some, if you want to do some aspects of theoretical physics. All right, so now the third example I want to go into, which is the one that is more related to more modern research that I've been involved in, is to try to define random mountains. So we all, have traveled, across on the plain somewhere, looked through the window, and we saw some mountains, and or geographical landscapes in general, but mountains are a good example. And then we look at it and said, well, okay, this looks like there's both a lot of organization going on, and our friends in geology and earth sciences will tell us all about it, that it's not random at all, and so on. But still, you look at it, it looks like something, was formed using some randomness. There is some, random shapes going on. And so now you go into the direction of wanting to define the natural way to choose uniformly at random topographic landscape. So of course, this, as opposed to the continuous functions and the numbers, defining what you call uniformly at random there, what are the constraints that you put on your topographic landscape, is important. And there are sort of different ways to construct what you would mean, a uniformly chosen random landscape. But the simplest one, it should combine two elements. First of all, of course, the height, the height of the height at a given point should be random, right? Should be able to fluctuate. But also, you don't want, you're not choosing the height here and next to you completely independently, because you want things to hold together, right? So you have this sort of two elements that, on the one hand side, things should be allowed to fluctuate, and the other side, there should be some sort of constraint that pulls things together. So the way I like to explain this to students when I start lectures on that type of graduate courses on that type of lecture or that type of topic is to say that the previous example of the Brownian motion, you could view it as the natural way in which a violin string would want to oscillate away from equilibrium. If you zoom in appropriately, you will see this vertical fluctuation of the violin string. Now, instead of, if you replace your violin string by something which would be like a huge trampoline, right, attached at the boundary with height 0 on the boundary, and in the inside it could sort of fluctuate, and then with little springs, that's how trampolines are usually made of, and then you just choose one position, random position of this trampoline that's going to give you like fluctuating heights all over. So the question now is, how are you going to, what do you get? So a first remark I want to make is that there are different ways to try to describe a random topography. The first one would be to say, well, topography is each point in a square, for instance, or in a disk, has a certain height, right? That's the way you like to think about it. So in some sense, you are choosing a random function from that to each point in the square associates a height. That would be a way to describe your mountainous shape. Now, there would be other ways to do that, which is like the way you do it when you buy a topographic map, which is to describe your landscape via its topographic lines, right? So you have, here the height is 0, there it's 10, then it's back to 0, then here is 10, then here is 20, and so on. If you buy you topographic maps, that puts the height differences at level 10. And so you sort of see that there are different ways to describe what this landscape is, to encode it in a different way. The collection of level lines or the actual function itself. So now if you do a simulation and you say, okay, let me try to see what happens when I look at a randomly chosen mountain defined in the disk using the appropriate thing at a fine mesh scale, and you zoom in appropriately until you actually do see something, then what you end up seeing is something like that. So what you sort of see with your bare eyes here, that's very rough, right? It looks like, so this is when you do a simulation on a fine grid of your mountain or you see these things with big spikes going up and down everywhere. And if you do what people who know how to handle simulation and would know how to do it, that means that you look at this picture and then you travel around with a little helicopter to see how it looks like from all aspects. You would see that the high spikes at the top and the low spikes at the bottom, they are very near to each other. And then you let the mesh of the lattice go, becomes smaller and smaller. And then what happens is that these spikes become higher and higher. And then what you realize after some time, and that requires some mathematical work, is that actually, yes, the object, there exists a limiting object when the mesh of the lattice goes to 0. But this limiting object is not a function. It's not a continuous function. It's not a landscape in the way you thought about landscapes. So the way you want to think about it is to say, well, it is this randomly chosen object, which is the random chosen way to choose a mountain in 2 dimensions, the natural object. And again, this one is really fundamental, absolutely fundamental for quantum physics. And this is the most elementary building block, this random function, in some part of theoretical physics. I'm talking to you, it has another name, like the Gaussian free field, or the free bosonic field, or this is exactly this object there. So it's not like just some exotic object here. You cannot code it as a random function. You can't say, if I give you it's not something that to each point in the plane is going to associate a given height. That's not the way, that doesn't work. So here we have an instance where you choose at random an object in a certain class that you see, yet you think you know, the class of random functions defined in the square, continuous function. And what you end up with is something which actually is not in that class. It's something else that you didn't expect to exist at all. But a typical uniformly random chosen mountainous landscape is not a mountainous landscape. That's sort of the outcome. It's something else. So what is it? So the clue is that there's a way to describe it, and that's what I'm going to tell you about is really research, modern research and probability theory that I've been involved in it, but the last 10 years or so, is that the right way to understand this object is via the topographic map. And the way it goes is the following. It has the following structure. First of all, so I'm just going to give you a descriptive picture of what this object is. First of all, there exists a very strange randomly chosen object, which you can describe easily. I mean, not easily, but you could see what type of object it is. This is just the disk with some punctures in it, like islands in the disk. The black thing is connected, right? So this is, you can travel on the black thing starting from the boundary all the way to the inside. So it's just puncturing at random holes inside this disk. Now, what you're going to do is that to view these holes here, instead of looking at the holes, you're just looking at these things. You look at these boundaries of these holes. They will play an important role. Now, this structure that I did draw to you here has one special property, which is not so apparent here, which is that the black object is a fractal, meaning that if I give you any given point in the plane, in this disk, it will actually be in a hole. So the black points have, in some sense, zero density in the disk. They are, and if I give you a point, it will almost surely be in a hole, but there will be always exceptional point that happen to be on the black stuff. Right. So now the structure is the following. You start with the disk. You choose one of these weird objects here. So these, you describe it by collection of loops. And now you view these loops not as level lines, but as cliffs. Meaning, on the outside of the loop, the height is 0. And on the inside of the loop, the height is either plus 10 or minus 10. And you do that independently at random for each of the loops. So it's like a little podium. You go up by 10 or down by 10. And outside, if you're outside of all the loops, you are at height 0. And then inside of each loops, you are going to repeat the same procedure that you're going to punch new holes here. And again, for each of these green things, you decide independently whether you go up by 10 or down by 10 compared to the height you had inside. So here, for instance, the level 2 loops here, you will either be plus 20 or back to 0 at the 2 steps. And then you iterate that all the way to infinity by adding more loops and inside loops, and you're at random. Now, if I choose a given point that I started, that if I start a typical point here, what you will see is that this typical point will be, surrounded by infinitely many loops, because at each step it will almost surely be inside a loop. So a given point will be surrounded by infinitely many cliffs. Each cliff go up or down with probability 1/2. So that means that the height of this particular point doesn't make any sense, because it's just the limit of this random walk, which goes up and down, the height of the different cliffs that are surrounding it. So the height of that point doesn't make any sense. On the other hand, in this way, by this nested sequence of all these cliffs, you have described an object that looks like something like a random mountain. And it is possible to show that this object that I've constructed in this way, if you choose this particular way of choosing these cliff lines, is actually a fair description of this Gaussian free field, which is this randomly, uniformly chosen mountainous landscape. So the idea is this mountainous landscape has a strange property, which is that it's plus minus infinity everywhere, the height, but still there's a way to organize things in order to deconstruct it in a way that we can make sense of and describe. So of course, I just finished at ETH a graduate course on the Gaussian free field, right? And it took me something like 50 hours of lectures, and the students are very good. And I could see that now the exam is going to arrive soon. The number of registered students who want to pass the exam has dropped significantly because they view this as a difficult one. And this description that I just gave to you with this height like that is out of the scope of this particular grad course. It's two, that would be for 2 more graduate course before. So what I want to say is not that it's difficult, it's more that you had no chance, right? I'm not expecting you to have understood anything precise about this Gaussian free field topographic map, except some stimulating your imagination in some way that might lead your brain resonate with some other things you have seen. It's the type of thing, on the spot you see, oh yeah, and then you go out of the room and say, what did he talk about again? And of course, the reason is also that there are a number of things that I had to be very sloppy about and not precise, and mathematicians don't like to do that. But of course, given the time constraint, that wasn't any other possible way to do that. So this is just to illustrate the fact that we are been dealing in our research with these very strange, funny random fractals objects, and these are conformal loop ensembles. There are not that many people in the world who know what these are and would be able to construct them rigorously, but we very much like each other, this little group of people who do, and because we like playing with these things, but also to emphasize the fact that it is really related to really fundamental questions. It's not like exotic things. Fundamental question about how to understand, basic building blocks in physics, and what is a boson, and these type of things that you learn at very early on in physics courses, that bosons have the property that they're indistinguishable, or these type of things. How do you make sense of that if you really want to scrap beyond the surface? But more generally, there is this idea that you have these 3 layers of possible surprises that you get when you want to study an object chosen at random in a very, very large set. And this last layer is the thing, you choose an object uniformly at random in a class A you think understand very well, and then you realize that actually the randomly chosen object is not in class A, it's in something larger. And a randomly chosen mountain is not a mountain. And of course, you have had things about exoplanets and all these things, and we all think we're surrounded by lots of things that have example of instances of things chosen somehow at random. But of course, we are the observers, so we are somewhere where the thing we observe around us is maybe not the standard uniformly chosen one, because we are actually here to observe it. And you could go on and on to try to elaborate on these type of examples. But of course, we mathematicians we are very modest. We just say, for these specific examples, these are, this is what happens. And there's this general idea that when you mix randomness with infinite sets, you can be surprised, and even our very clever friends in theoretical physics could be surprised as well, because some elements of this mixture between randomness and continuous are really counterintuitive. All right. There are, in contemporary mathematics, this general theme of choosing a mathematical object at random is really something that is around a lot. I chose the examples of numbers and functions, and because this is something that everybody could understand. If I tell you I choose at random a group, I would have to define what a group is, and I have to explain you how this works. But that's again, what a typical random group is also a very sensible question to ask in a mathematical perspective. And if you look at the work of say Manju Bhargava, who's working on the some of the most abstract mathematics about prime numbers, elliptic functions, and something like that, one of his main results is 100%. The proportion of elliptic curves satisfying these or that properties is actually 100%, meaning that a randomly chosen elliptic curve will have certain properties. So it is this type of theme is something which is not it's not specific to certain questions. It's a very natural way to proceed. If you have a class that you don't understand well, try to understand what a typical element, randomly chosen element in that class is. Okay, so I see that my time is out. I don't know by how much, but I will stop here and thank you for your attention.
Thank you, Professor Werner. I think we will just have a very short Q&A session that Professor Harms will be moderating.
The idea is that you join us. So we'll have a very limited amount of time for questions, but is there anybody in the audience here who would like to ask a question? Yes, here.
Can I ask a question?
Yeah.
Actually, I do research in probability theory, so I have a lot of questions. But actually, maybe one will be, like you said that in the CLE, if you choose randomly a point, there will be always a pole. But I didn't understand it. Like, could you explain why it is so?
I mean, the way things happen is that it's a little bit the same story as when you choose a point uniformly at random in the interval 0, 1. If I give you a specific point in advance, you know it will not be chosen, right? Because that's just has 0% of falling exactly there. So this black structure, right, this black fractal that I defined before, has 0 area. It's random and has 0 area. And because it has 0 area, it has the property that if I give you a given point, the probability that it will be in that black thing will be 0 because the thing is too thin. That's what I had in mind. Therefore, it is in the hole.
And then my other question is that actually I'm particularly interested in the self-avoiding work.
Yeah.
And I mean, it's well known that it's very hard and very little knowledge about it. And one reason I can think of is that it's compared to the simple random walk, which can be modeled by maybe like binomial process, and the self-avoiding walk doesn't have any model to fit in. But is there any other reason why it is very hard? And actually, your work in the stochastic loner evolution is the mean to use for it. So I actually like to know.
So usually I give long answers to questions, but in that case I will give a very short one, which is that your question is not related to what I discussed, but what you read about what I did before. So I'd rather not answer to your question here, but because most of the audience wouldn't really see what it is about. The general question is that there are ways to choose at random curves with some constraints, which would be the curve is not allowed to self-intersect and things like that, and that's things that we'd like to look at, and these are very difficult questions, but it's not directly related to what I said here, so maybe I'll just postpone the answer to some other
things. Thank you so much. I'm just so interested.
No worries.
Thanks. Maybe there's one more broad question that I got from online, and that would also be a nice way of wrapping things up. Maybe the question is, how can non-mathematicians, but the scientists working in other disciplines, profit from the logic and creativity of mathematicians? Would you like to comment on this? We function, it's true that we function somewhat differently, but I don't think that we are that different, of course, because, the way we choose our, careers and things like that is a bit, we chose to go into math rather than in physics. In my case, I don't think there was any deep reason why. So when I talk to my friends in physics, the answer is no there. Well, actually, maybe yes, because I had a very, very nice school teacher at primary school who did teach us how to trick this. But we are how we are. We try to, one thing that is, I think, common among mathematicians, that we try to be very honest and try to be very authentic and remain true to our ways of functioning, and to say also there's one aspect about mathematics is that still, it's a little bit like a sport, brain sport. And as you know, the world champion in chess after, Carlsen now at age, in his early 30s say, I'm getting too old, the younger ones are faster than me. And so of course there are ways to compensate. You can be a very good mathematician when you grow older, but you always are humbled by the fact that, the younger people always come and they will run faster than you very, very quickly. And so that we have to remain modest, and you pass the baton to the younger generation early on. So, when we tell you about the old stories, how it was, I discovered this and this, blah, blah, that, in mathematics, the young students will say, okay, I read your paper, I understood it, what next? I want to, continue and start where you left it. And so all these things, we try to be, authentic and honest about things. That one important thing is this general idea that, among us, right, we know that these things with prizes and genius, or because sometimes from the outside world, the mathematicians, Fields Medal sort of comes with some aura of something special. Okay, among us in the community, we know that's just this PR machine, to have some people which end up, being here and having to tell you something. But we are a large group of people who like doing what we want to do, what we're doing, and chose to do that rather than to earn a lot of money doing something else. And we're happy with that, and we know what we're talking about, and when we're between us, we know that there's nothing more into it that what we're talking about. And I think that just be authentic like that is always just the best thing we can show to the outside world, and also to our friends in other parts of sciences. So the creativity part is, it's not specific to maths, it's everywhere. There's always this moment where at some point you need to try out something and goes in your brain, and it's also not necessarily in science. In everybody's life, we have to be creative in making our life choices, and that's just the way life is.
I think, unfortunately, we need to wrap it up. It was great. Let's give an applause to Wendelin.
Thank you, Professor Werner and Professor Harms. Next up, we will be having our lecture by Professor Fraser Stoddart, but we need a couple of minutes to set that up, so just give us a minute. I'm just going to take the opportunity to share with you a quick rundown of the rest of the afternoon's program. So after Professor Stoddart's lecture, we have with us Professor Dr. Markku Ilaila from the Technology Academy of Finland. He will be giving a short presentation on the Millennium Technology Prize 2022 and 2024. After that, I think some of you will have your small group sessions. We have one with Sir Tim Hunt that will be at Think Tank Room 19. Sir Andre Game will be at Think Tank Room number 20. And Professor Hartmut Mitchell will be at Think Tank 21. For our online participants, you will be having yours with Professor Alessio Figali on the Give Me platform. After that, some of you have signed up for the social programs, for the tours that are going down to Chinatown, Little India, and the rest. We have more instructions for you later on, but basically, when you're done with the small groups and the afternoon break, if you have time to grab some food, we'll see you at the registration area. There will be ushers there to bring you to your various buses, and you'll be going on your tour of Singapore after that. Okay? So just a couple of minutes more. Professor Fraser Stoddart will be giving a lecture today about the recent advances in the design and synthesis of molecular motors and pumps. Now, Professor Stoddart is the Nobel Prize winner in chemistry in 2016. And I believe we're almost ready. The Q&A will be moderated by Professor Zhao Yanli thereafter as well.
Not on the screen.
Yes. Let's welcome Professor Stoddart.
Okay. Well, I'm delighted to be here. It's great that the GYSS has become live again. I will always look upon this as one of the highlights of scientific engagement between we older guys and the young people out there. The second point I want to make is that, believe it or not, there is some major relevance between the talk that you did hear from Professor Werner and what I'm going to talk about. But first of all, I'm going to use a first slide and in 30 seconds cover 30 years. So in 81, we had looked at a concept called second sphere coordination. This is a transition metal complex bound by a crown ether. The same crown ether binds a wipeout weed killer called dipod. And the other part of the wipeout weed killer that was marketed by ICI in the 1980s is paraquat. And just by shifting some atoms around, we were able to complex paraquat inside a crown ether. This led to the emergence of the so-called little blue box in 1988, and that set the stage for the first donor acceptor catenane that we reported in Angkor-Wat-Kami in 1989. In 91, we described a molecular shuttle in JAX, and this was the first time that I actually mentioned the terms molecular machine. We turned this degenerate system into a non-degenerate system in 94 and made a molecular switch. We put many rings together, again, because there was a lot of questioning about were we actually able to put rings together. So we just said, let's put 3, 4, 5 together, and the community will perhaps be persuaded. We had a switchable catenane by 98, and I'd already moved from the United Kingdom to the United States, to UCLA, and we teamed up there with Jeff Zink and put some drug delivery systems together based on these ritaxane switches, and using same ritaxane switches with Jim Heath in the area of molecular electronics. And then there was a big intellectually disruptive discovery made by a postdoc in my group at the time, and we found that you could take this blue box with its 4 positive charges, that we could take paraquat, or I'll call it methyl viologen, 4 + 2, 6 charges. You didn't expect to be able to make a complex, but if you killed 3 of these reductively, by putting in 3 electrons, you got a very strong complex. And so that's now the basis for today's talk, because this gives you a huge amount of oomph in making molecular machinery. So pumps through the ages, if we start at the bottom here, our own bodies are replete in examples of microscopic bimolecular pumps, and these are 3 examples along the bottom, and they go back, of course, millennia. Here in the middle, maybe 7,000 to 8,000 years old, are macroscopic pumps, including the famous Archimedes pump, and then at the very top, the ones I'm going to talk about today, namely nanoscopic molecular pumps. And so the first message I want to get across is it's night and day between how these macroscopic pumps work and how both the biomolecular ones and the artificial ones work. So if we look at the top of this slide, if we want to move something, it could be a car, from here over a mountain to there to here, then that is the mechanical approach. The landscape doesn't change. If we want to move, make this now, say 25 molecules from here to there, then whether it's in the bio world or in the artificial world, it's all about the landscaping and Brownian motion. And that's the first link I have with the mathematician, Professor Werner, that spoke before me. So we're depending a lot on thermal energy to get from here to there. Here is a necessary concept. in order to be able to make a molecular pump. That is to use a flashing energy ratchet so that you get directional movement across a so-called dumbbell. And this is it defined down here in a chemical context with a ring which is defined there. And you can see that under a condition of oxidation, the blue rings come on. They will go over the neutral end, preferably than over the charged one. And in so doing, they will go into this well. And now you change the landscape. If you reduce the molecules, then the well goes up and the mountain in front of it comes down. So again, you heard about adjustable mountains in the last lecture. To summarize this situation, on the right, you can see that if we have an oxidative state, we have a binding between the donor and the acceptor here. And when we reduce, we remove that, and the ring can move over the right-hand side. And the energy profile is shown underneath. So again, let me emphasize the importance of the introduction of this radical chemistry, taking two components with 6 positive charges, reduce them, put in free electrons, and bingo, you have a very strong one-to-one complex. And here is a thought experiment. If we reverse our dumbbell through 180 degrees and we have the charge component on the left-hand side, we can envisage a situation where the reduced ring will form a complex by going over the charged component because it's been reduced. And after that, we will get relaxation. And a lot of Brownian motion is going on here. We get to here, and then we oxidize. The well goes up, and the mountain comes down, and the molecules, i.e. the rings, move off by the right-hand side. So the key factors in the design of these so-called non-equilibrium systems is, in our hands at least, a highly stabilizing radical-radical interaction between so-called bipyradical cations and these rings as dicationic diradicals. Contrast that with when they are fully oxidized and there's all the charge there. You've got strongly destabilizing Coulombic repulsions, and it is this redox property that allows us to go on and design the molecular pumps I'm going to describe to you, depending on not thermodynamics, but the kinetics of association and dissociation, which you can adjust or modulate. So here is the roadmap that I'm going to use. If I have time, I'm going to put something in that's quite different, because I don't want to come over as just a one-trick pony. We will start then with our first molecular pump, call it Mark I. And in a cartoon format, here you see it. You see the familiar so-called blue box on the left-hand side, and a dumbbell with various species to it, a charged end at the left, a bipyridinium site for recognition under reduced conditions of the ring, and what we call a steric barrier or a speed bump before we push the ring onto a collecting chain. And here is a movie. I will define the system chemically in a minute, with the rings coming on under reduction. And as you oxidize, they go, the second one, to join the first one. And if we let this replay once again, you will notice, very interestingly, that once you get one ring on to the collecting chain, when you reduce at this point here, it will want to come back. And so the speed bump serves a very, very elegant purpose of preventing that happening. And that allows you to put on multiple rings, and that becomes important. And I can go down the right-hand side here, showing how reduction oxidation, Brownian motion under thermal control, reduction, and oxidation, and a more Brownian motion under thermal control gets 2 of these rings onto the collecting chain on the right-hand side. So here's the chemical constitution of a system that moves away from equilibrium. We're just going to use some proton NMR experiment signals. The experiment was done at above room temperature at 42 degrees centigrade. We carry out the redox cycle. One of the things we do use is zinc dust to do the reduction, followed by nitrile hexafluorophosphate to carry out the oxidation, and all that can be done in 10 minutes. But then we've got to wait an hour and a half for the rings to make their way over the speed bump here, and these high field signals show eventually that this ring is sitting on the collecting chain. And we can repeat this process and get 2 rings on to the collecting chain. So again, using a movie, you can see that we're moving away from equilibrium as we go down in this vertical direction. The first cycle is pretty efficient at 90% overall. And what is important on this slide, you'll see, is this free energy of activation at 23 kilocalories per mole to have the ring pass over the speed bump onto the collecting chain. And a little bit less efficient, but nonetheless it happens. But notice within experimental error, we're getting the same barrier as we got for the first ring. This means that we can put multiple rings over. The presence of rings on collecting chains do not inhibit these rings coming to join them. You will see multiple numbers in a minute. So we increased the efficiency just in terms of the time scale. You'll see the work was now done at room temperature. We did some changes to the constitution, very subtle ones. We removed a carbon atom there, and that increased the coulombic repulsion between this and ultimately the ring when it was on the part here where we're oxidizing. And after the redox process, it took again an hour and a half to go over onto the collecting chain. But if we are to extrapolate up to 42 degrees, which I showed you for Mark I pump, the Mark II pump was happening in minutes. So that was an increase in speed. And I want to introduce you to what I call the molecular joule and Jewett pumps. So the joule pump is really designed so that we're looking forward to a future where we put this into the surface of a vesicle and be able to pump rings from outside into the internal part of the vesicle. And so we can take this chemical constitution and starting up here, the ring can be brought on under reduction conditions. Oxidation, we actually are able to isolate this 2-rotaxane. This is 1 ring plus the dumbbell, hence the 2, and then carry out a reduction and force the ring off the right-hand side. So again, it's a unidirectional motion. And here's a movie showing what is happening. And as this goes on, I just want to point out that Yun Yan has just joined NUS as an assistant professor in the last 2-3 months. And here you see the ring going over to form the 2-rotaxane and then being reduced and oxidized and coming off the end. So we have this prototype, if you like, to be able to have something put into the surface of a vesicle. The Jewett pump is an example where we have these, we now call them pumping cassettes at each end of a linear molecule. This one happens to have 36 methylene groups interacted symmetrically by positively charged nitrogens with 2 methyl groups on them. And you can see that in the course of time, we can get 4 rings on and make a 5 retaxane. And this we did not using chemicals, but electrochemically with electrolysis set up with these conditions, and a period of time when we're reducing, and then a period of time when we're oxidizing, and we can recycle. And here is the spectroscopic evidence for the purity of what is a free retaxane with 2 rings on the dumbbell. We can repeat the process as you saw in the movie and get 4 rings, that is 5 retaxane, and again, it's a very well characterized compound. Okay, so we could get up to 5. Can we go larger? And so under the title of a precise polyretaxane synthesizer, this long dumbbell was made. There are many atoms in here. This unit is repeated 50 times. The number average molecular weight is around about 2,000. It's fairly homogeneous, not entirely, but fairly good. And that is used to pump on chemically to begin with, 2 rings, 4 rings, 6 rings, so that we have a 3, 5, and 7 retaxane that get fully characterized by integration in the proton NMR spectrum. It's very precise. You can see the numbers, for example, 47.45 with the expected 48 there. They're very, very close to what we expect. And again, a movie showing that we can have 2 rings come on from each side of the long polymer chain with its 2 pumping cassettes, and then we can bring on another 2, and I'm going to speed it up so that I leave some time, hopefully, for questions. And we end up with some 12 rings. At this point, we have pushed our luck as far as we can go because of the length of this ring and the massive coulombic repulsion that is being built up here. So you have really built up a system that is miles away from equilibrium. And so with the 2, 4, 6, 8, 10, 12 rings, you amass up to ultimately 48 positive charges, but let's count these 2 on the end. We can't not count them. So we have a total of 52 positive charges. And I always throw out a challenge to the community here. If there are battery people, I think we have the makings fundamentally of all organic batteries being produced by these compounds. If we take a higher molecular weight polyethylene glycol chain, then we can push these numbers up further. Here's 4 rings with 5 retaxane. And now we're doing it electrochemically with these conditions here. And here you can see that it's got up to 48 rings with 49 retaxanes. And you can do this in a couple of hours. It's amazingly efficient. And it always comes on 1 ring from the right and 1 from the left in unison. And here you see the PEG 5000 with a 9 and a 13 retaxane, going up eventually with 16 rings, 20 rings to a 17 retaxane and a 21 retaxane. So the take-home messages so far are that we can control the synthesis of polyretaxanes through an autonomous electrochemical approach using artificial molecular pumps. The installment of 20 rings onto a linear PEG chain of 5,000 gives us 86 positive charges. And the last one you saw, a star polymer, we can get up to 20,000 with almost 350 positive charges. So it depends on the efficient operation of what are called these pumping cassettes, and the important concepts are here are that we're dealing with kinetic asymmetry in the context of not in, common or garden thermodynamics, but trajectory thermodynamics. And so what do I mean by these terms? Kinetic asymmetry is an evolving property that allows the selection of a preferred kinetic pathway for determining non-equilibrium behavior. And trajectory thermodynamics is a theory in which the focus is placed on trajectories rather than states when it comes to describing how both biological and artificial molecular machines work when driven by either chemical fuels or electricity. And these trajectory thermodynamics have shed light on how pumping cassettes can be designed to allow the input of energy to drive thermodynamically uphill by pumping rings into a non-equilibrium type system. So, let's go back to our roadmap. Now, we've done all this in solution. Could we put it onto a surface? Yes, we can. So, here is a metal organic framework. It's two-dimensional in area. I just show the top surface here, can have grafted onto it these pumps with pumping cassettes at the top. We can easily, for the length of the pumps that we have, put on up to 5 rings here on the various different pumps using these redox reactions that I've described before. And then we can simply de-thread by cutting them off at the bottom with some acid, because it's a carboxyl group link that we have here to a zirconium-based MOF. And under alkaline conditions, you can make the various pumps attach themselves to the MOF, but under acidic conditions, you can remove the pumps from the metal organic framework. And so here's just an image of going through the, start with the base, making the stalks on the two-dimensional surface, and then adding these rings until you get up to 5, as it turned out in our experiments, and then release them by cutting the stalk off at the bottom. Of course, what's on the bottom is here, or what I should say on the top is also on the bottom of this two-dimensional metal organic framework. And so you can go through an even more complicated scenario where you see rings coming on from the top and from the bottom. And again, you can remove these very easily at the end of the day. Again, it's a flashing energy ratchet mechanism, and it leads to a very important breakthrough in, I think, conceptual science, in surface science. But before I go there, if we start here, you can see that under the first set of conditions, we have brought these rings onto the stalks, and then we carry out a reduction and then an oxidation, and during that oxidation process they go over the speed bump in the context of the stalks on the MOF, and then we carry out an oxidation, and I go as far as show you that there are 2 rings on each stalk here, and we express the accumulation of away from equilibriumness, if you like to call it that, by just using these concentration numbers. So if this is 55 moles per millimoles per liter, this is 111, and so you, every time you're adding on roughly 55, and you're just pushing the energy up and up. So what we found exciting about this work is the fact that for about 100 years, the chemistry and physical communities have been well versed in physisorption, somewhat less, maybe 70 years in chemisorption, and now we can add another form of as option to this list, which we call Mechanis option. And the distinction is that both Physis option, with weak van der Waals forces being the driving forces, and Chemis option, where we've got electronic interactions, and so they're much stronger, they're both under equilibrium control. But the one that I've been showing you is a non-equilibrium system based on the formation of these mechanical bonds. It's highly selective, and it's very easy at the end of the day to go from the very high energy system back to a multi-layer that has lost its rings. Okay, so Physis option, Chemis option, and Mechanis option. Finally, I want to, as far as artificial machines are concerned, mention the electric motor that was actually molecular motor published in Nature last week. And it's a simple design. Largely, we took the building blocks for the linear molecular pump and built them into a large loop. And so here you can see the speed bump. It's the same one as we used in the linear system. Here is the pyridinium charged head. Here are the bipyridinium units. And the familiar, of course, little blue box. And if you start at under reducing conditions, then you can move the ring onto these two bipyridinium radical cations at, say, 12 o'clock and 6 o'clock. If you then, having carried out that reduction, and have these two tris radical complexes carry out an oxidation, then the rings move back to 9 o'clock and 3 o'clock. And you can see that, again, we can use NMR spectroscopy to really identify every detail of the structure of this fairly complicated molecule. And we were graced with getting one crystal structure of the reduced state when this reduced ring is on the 12 o'clock and 6 o'clock positions. There's our crystal structure. And again, I can show you the right movement around, starting up here, of these two rings. And you can see them go from 3 o'clock to 9 o'clock to 12 o'clock to 6 o'clock under reduction and in oxidation, back eventually to the starting point here, except that we're only halfway around. We've only done a 180-degree cycle here by the end of step 3. And by going on, we can complete it in a cyclic way. And what I've taken out are, we used deuterium labeling to follow the fact that the two rings are identical in constitution, but if we deuterium labeled one of them, we could ascertain that we had a 360-degree rotation after 2 redox cycles. And so here's a movie, and you can see the rings under reduction going to 12 and 6 o'clock, under oxidation going back to 9 and 3 o'clock. Okay, so how does that compare with what's out there? David Lee in Manchester, a former student, a few years ago published in Science a very similar system where he has 2 rings on a loop, as I would call it, and these were the conclusions from his work. I point out that since it's chemical, there are waste products. We don't have any waste products because it's powered by electricity. And the time scale of ours is very, very much shorter. What took him a day, we can do in a few seconds electrically. The interesting thing about this publication was that it was, as it were, taken over by the pandemic. And so the message I may want to get out to the young people is because some people say, Fraser, Stoddart, it must be easy for you to publish in Nature. No, no, no. Notice it. 4 years, right? It was an uphill battle. And I won't go through the various stages. I will just point out that somewhere along the route, it went to Science. And they didn't even put it out for review. Eventually, it went to Nature, and it was accepted. We got the proofs in August, but it took them 3-4 months to publish it. So everything was slow, but we got there. So in summarizing, we have kinetic control of these artificial molecular machines. It's all about kinetics, kinetics, kinetics. The driving force is this radical chemistry that we stumbled across belatedly, and the pumping cassettes that take us away from equilibrium are key to getting both this new concept of mechanisorption and the electric molecular motor that I've shown you. Now, this is not about me. It's about some amazing young scientists. And here are some of the people who were around at the time that we broke into the radical world. And all but 2 of them are in academia. I don't have time to go through all of them. Hao Li, for example, since we're close to China, is in Zhejiang University. Chuyang Chen in Xisheng, and so it goes on. Kan Kai has just gone to Nankai. The work that I described to you with the molecular motors was done very much in a collaborative way, and I want to add that 95% of my research has been done collaboratively. I enjoy it. It's an enormous opportunity to interact with your colleagues and do things with them that they can do better than you. And the eventual outcome is a very, very much better situation than you could do alone. And a great driver in all of this is physicist Dina Stumian up at the University of Maine. There is no one in the world, in my humble opinion, that understands the operation of biomolecular motors and their artificial counterparts better than Dean. And we've been privileged to have a huge amount of Zoom time with him during the pandemic. The radical scientists of now are there. As I said, Yunyan has just gone to Singapore. Qinghui is at Zhejiang University along with Hong Lang. Let's see. Chaoyang Chen is going to Hong Kong University, and Yang Zhao is on his way to Peking. And that's what gives me, I think, more satisfaction in the research, the success of these young people tackling not easy problems, but rather tackling problems because they're difficult. Outside my own group, of course, there are the 2 fellow Nobel laureates, Jean-Pierre Sauvage and Ben Feringa, and we have very friendly interactions and have done over decades with these 2 incredibly talented scientists. Others that we've worked with or been close to are included there. Very dangerous slide because, and that's why I move it off quickly, somebody will be sitting out there saying, why is my name not up there? Well, there's only a particular amount of space. Other general comments I want to make is that of late, well, from 2015 through to just a month ago, all of these people that are pictured there have made their comments about the progress of the design and synthesis of molecular machinery in various different journals. Most recently, Carsten Bruns in Nature Nanotechnology. Okay, so does this 8 minutes mean that I should dry up, Yanli, or can I take more? 2 minutes? Okay. So as I said, I just want to make the point that my life is not all about molecular machines. It's a small part of our activity. So here's just an example of a bit of breaking news. In 2010, we were visited by serendipity. Here is something called gamma-cyclodextrin. 8 glucoses joined up in a circle, if you like. You take a spoonful of sugar, you take a pinch of salt, you take a swig of alcohol, and in British parlance, Bob's your uncle, you've got it. You get this extended CDMOF framework. And this has led to a startup company in, of all areas, skincare. And it was launched just before the onset of the pandemic. And it's going extremely well. That's all I will say. But this summer, I lectured at the Chirality meeting in Chicago. And I met up with Daniel Armstrong from the University of Texas at Arlington. And in contrast with the cyclodextrins, he told me that microbiologically, he could make cyclic fructans. And he showed me the structure. And I couldn't look at those without seeing a crown-ether type constitution in the middle there. And so I said, why don't you send us some? And he sent us some. And Yongwoo from Peking University, amazing carbohydrate chemist. He's made polysaccharides with over 180 residues in them for his PhD. He took this, a spoonful of sugar, CF6 this time, a pinch of salt and a swig of alcohol, and lo and behold, he gets CF MOFs. And so they're assembled just like the cyclodextrin ones. And so we now have 2, and there are only 2 of these metal organic frameworks in the world that are genuinely green, edible, whatever other adjective you want to put onto them, because most of the rest, as you know, are laced with transition metals. And it is the spheres that represent the void space that are important in giving these CDMOFs their character to store small molecules. And now we can anticipate the same scenario for CF-MOFs. A couple of slides just talking about philosophy, because he's a fellow Scot. Alexander Graham Bell. Notice what he had to say if you visit the former Bell Laboratories in New Jersey. Leave the beaten track occasionally and dive into the woods. You will be certain to find something that you've never seen before. My own take on it is head out as a young person, if you possibly can, and do your own thing. Because to achieve something that is impactful in contemporary science, and to be singled out as a scientist who leaves their mark on science, and ultimately technologies, you need to become recognized widely as having done your own thing. This goal means that you make, and this is very important, a conscious decision to sum up enough courage to tackle what I would call a big problem for which no one has provided a satisfactory answer. Conclusion, tackle big problems and be driven by curiosity and almost nothing else. Thank you.
Dr. Werner, thank you, Dr. Stoddart. Professor Zhao will be moderating the Q&A now. Unfortunately, as we're running a bit short on time, we only have time for 2 questions. Do keep it short so that we can wrap up in time for the small group sessions as well. Professor Zhao, please.
Yeah, highly inspiring talk by Fraser regarding molecular machine and the switches. Any questions? We only have time for 2 very short questions. Yes, please.
Thank you, sir, for the very nice talk. So molecular motors are, of course, fundamentally very interesting, and you have been going for this smaller system to the larger system now. So where do you aim, or where do you think is the ultimate goal, going from smaller motors now to the larger systems? Where do you think are you actually heading to? Like, what is the ultimate application could be for this kind of large systems?
To be very honest, I don't give a damn about applications. I am effectively driven scientifically by addressing fundamental issues. There's far too much out there in the media about what are the applications. And I'm sick and tired of, over several decades, dealing with the media on this subject. And I always end up by saying, I'm a professor. The output from my laboratory is not necessarily molecular machines or CD MOFs or CF MOFs. It is young people that go on in their own environments to be incredibly creative, because I've spent and enjoyed spending so much time with people roughly aged between 18 and 32. That is my main output. I look back on it. It's much more important than what are the applications. And nowadays, I don't drive the research program, the young people drive it. I'm in Singapore.
Yes, please.
Hello, thank you for this insightful talk. So as a biophysicist, I've always been fascinated by, let's say, biomolecular motors, the ones that move in cells and, let's say, transport vesicles across microtubules. So do you see possibilities for the electric molecular motors that you've shown to, let's say, put external load on them and make them, let's say, transport things?
Of course, I think, you know, this is just like the birds and the bees and the bats. They have been flying around for millennia. It's only in the last, what, 120 years, if we go back to the Wright brothers. And let me just interject that fellow Scot physicist Kelvin, Lord Kelvin, towards the end of his life said there would never be manned flight. Ha, ha, ha. You got it so wrong. And so again, it's very difficult to predict. I'm not going to say they are going to have the same impact if we take the electric motor at the molecular level that the electric motor is having at the macroscopic level today. We've gone through the time of the food mixers and the hair dryers, and now we have electric vehicles on the road and so on and so forth. But you know, it's taken 2 centuries for that to happen, because the first steps were taken by a few physicists in the 1830s, 1820s, 1830s. And it did in fact take half a century before the first hair dryers and food mixers came on the scene, let alone electric vehicles. So I don't know how many decades it's going to take, but I predict that one day, both in material science, and I'll leave that just with these 2 words, but in medical science, there will be a revolution that will be akin to the way people have hip joint replacements. And I've just had a heart valve replacement, a so-called TAVR, in the last 18 months. These are amazing things that are happening at a macroscopic level, and they don't get the publicity that, oh, we're going to solve the problem of cancer. Ah, come on, you're not. That's a big, big, big problem, and it's going to take a long time. But the medical profession have made great advances in replacing joints and hearts and all the rest of it. So it's just a matter of time before I think they look to these artificial molecular motors to perhaps aid and abet the performance of the biological ones. But there's a lot of development to go on there, a lot of dreaming, and a lot of challenge.
Okay, thank you. Looking forward.
Yeah,
All right. Please feel free to discuss with Fraser during break. Thank you so much. I also want to thank Fraser again for his wonderful talk. Thank you.
Thank you again, professors. Thank you again for staying with us. I would now like to invite Dr. Markku Elila to just give us a short presentation. He is the CEO of the Technology Academy of Finland, and he will be presenting on the Millennium Technology Prize. Dr. Elila, please.
So good afternoon, everybody. I will be quite brief since I'm the person between you and your free time activities. But to get started with, I'd like to thank the NRF for inviting me to this wonderful event, and also for inviting on a continuous basis winners of the Millennium Technology Prize as speakers here. As you may know, 3 out of the 20 speakers here during this week are winners of the Millennium Technology Prize, so I'll briefly tell you a little bit more about the prize and introduce the latest winner of the prize, and then tell you what is happening in the next couple of years. So, the Millennium Technology Prize is kind of supplementing the offering of this event by bringing you people that have done work based on science, but have come up with technological innovations that are already commercially in use and accessible worldwide. So, the home of the prize is in Finland, and it is our tribute to innovations that are done on a global basis. And we want to highlight the importance of technology in tackling the great challenges that we are facing in this world today. I mean, things like Earth's resources, the climate problems, biodiversity, and the ability to combat pandemics are so important that we want to recognize all the great achievements in those fields. The prize is 1 million euros, and it was first awarded 19 years ago. So next year, when we are awarding the next prize, we will be celebrating our 20 years of existence. The patron of the prize is the President of the Republic of Finland, and maybe for those of you who are not aware of the political system in Finland, we are a member of the European Union, and our presidents have a partly ceremonial role, but the president is also responsible for the foreign policy of the country in collaboration with the cabinet of the Prime Minister, who happens to be a lady at the moment who's 37 years old, and she's doing a very good job in this very challenging world situation. Going forward, I'd just like to show you the faces of the persons who have won the prize over the years. Out of these 12 individuals, 3 of them are speakers here during this week. I will start with the oldest winner. In 2004, 19 years ago, the winner was Tim Berners-Lee, who has invented the World Wide Web while he was working at CERN doing particle physics. I was at CERN at the same time with him doing my PhD, but I didn't do things quite his way, and also was not involved in the academia for another 25 years before I came to this job with the Technology Academy Finland. The second laureate was Shuji Nakamura, who developed the capability of making blue and white LEDs, which has led to, enormous energy savings in the world over the years. So it's a part of the, you know, the lighting systems today are largely based on LEDs, and the energy that is needed for lighting up the globe has been reduced considerably due to his work. Well, yesterday you heard the presentation of Robert Langer, so I don't need to say more about that. Then another person who has several times been here in Singapore for GYSS is Professor Michael Grätzel, who was a major character in further development of solar cell technology. Then the next one was Shinya Yamanaka in 2012, and he has been one of the pioneers in ethical stem cell research. During the same year, in 2012, the other winner was Linus Torvalds, who is the developer and continues to be the father of the Linux operating system, which was mentioned yesterday in the supercomputer presentation, being the basis of all supercomputers of the world. And also Linux is the basis of the Android mobile phone operating system. In 2014, Stuart Parking, who will be speaking here tomorrow, won the prize. And then Frances Arnold, who was working on directed evolution, got the prize in 2016, and then consequently she also got the Nobel Prize in Chemistry in 2018. Tuomo Suntola has been the developer of the ALD technology, which is atomic layer deposition technology, which is used in semiconductor industry, making microprocessors and mobile phone electronics largely. So that's the basis of very much of the communication and computing technology of today. Then David Klenema was the speaker here 2 days ago, and he won the prize last year. The prize is the 2020 Millennium Technology Prize, but because of the pandemic, it was only awarded last year. So he got it together with Shankar Balasubramanian for the next generation DNA sequencing technology. And the latest winner who got his prize 3 months ago in Helsinki is Professor Martin Green from the University of New South Wales in Sydney for his long-term work on solar cell technology. And he will be telling a little bit about that himself. I hope he will also appear in the near future at this event.
I tended to do best at subjects that were difficult to understand, and you have to put in a bit of effort just to understand what the lecturer was talking about. And you know, one of them was semiconductors. It takes a fairly large barrier to understanding even the basics of the field. That as I grew a bit older, I was looking for something with a bit more social impact, and I realised that my the photons. So ideally you get each photon that strikes the solar cell that has sufficient energy, creating an electron in the electrical circuit that you connect between the top and the bottom of the cell. And in that way you convert the light into electrical current. I won a Commonwealth Scholarship to study in Canada at McMaster University, and my new thesis supervisor was showing me around the labs, and one of the other PhD students was measuring a device, and the professor who was showing me around said, and we put a black cloth over it because otherwise it responds to light like a solar cell. And, I found that the devices being studied were really ideally suited for use as solar cells, and that started me in a direction that gave me a unique approach upon the field. My PhD thesis work proved very important to my subsequent career, in that the devices that I was working on for my PhD proved to provide another way of making a solar cell that hadn't really been fully explored before. NASA in the US had launched a program to try and improve silicon solar cell efficiency, mainly for their space cell program, and we were able to show that we were doing better than all the NASA contractors in terms of the voltage we could get out for a given amount of light being shone onto the cell. For that 25% efficient cell, we use what's called the PERC cell, P-E-R-C. That's an acronym that I personally invented along with the cell. We realized that the surfaces of the cells were very important, and that's the area where improvement could be made in earlier cell designs. So we paid a lot of attention to improving the surface properties of the cells, and the structures that I'd been working on for my PhD proved very effective for doing that. That passivated emitter and rear cell, or PERC cell, it's now taken the world by storm. The third big contribution we made was the students that we trained along the way. So I have now supervised 120 PhD students in my career, but many have gone on to do wonderful things within the industry. Yeah, I'd talk about the flapping of butterfly wings, because it's, when you look at all the events that had to line up for the industry to evolve in the way it has, it was just serendipity upon serendipity that got us to where we are now. I think the pace of change is going to accelerate, but the world will, over the next coming decade or two, shift to solar energy and wind. So a huge transformation of historic significance underway at the moment.
Okay, moving on, I'll just give in a couple of words, tell you about the events in October, and then go on to say a few words about 24. So the event took place in Helsinki in October, and we have a Lappish Sami cultural program, where you can see Northern Lights being reflected on the screen. And here you can see the President of Finland, Mr. Sauli Niinistö, handing the trophy to Martin Green. A couple of words about the events. Otherwise, we organize these events every 2 years, and there's always a conference involved, and it's called the Millennium Innovation Forum. And we organize that together with our corporate and governmental and academic partners. I think what we can just say that it was an exciting event, and we had experts from all over the world talking about relevant topics like the green transition, the digital transformation, and resilience. We have also gained quite nice visibility for the prize during last year. We were covered by press or media whose reach was more than 1 billion people. Our reach in social media was 53 million. We were also streaming live, and that was could be seen globally, and there were about 1,700 articles written about the prize across 37 countries and all continents. And then a couple of words about the statistics, what kind of nominations we get. The prize is based on the nominations that we solicit from all over the world. Last time, if we look at the different technologies, the nominations were from life sciences, they were from ICT and smart systems, and energy and the environment. There has been quite a large drop in the number of nominations in the field of new materials, processes, and manufacturing. Hopefully that will also increase in the coming round. Here you can see the geographic distribution of the nominations. The largest part are coming from Europe, followed by North America, and then Asia Pacific. And the gender distribution of the nominations, the nominees were until 2020 almost exclusively men, but we paid a lot of attention to attracting also candidates being proposed who are women, and we were quite successful in that, so that almost 30% of the nominees were women. Here's a quick look at the schedule for the next round. So we will start our call for nominations in the beginning of April. We have been handing out these bookmarks during the event that you could take back home and think about people who would deserve to be nominated, maybe propose to your supervisors or the departments at your institutes and universities to make good nominations. There are many people who would deserve this who have never been nominated for this prize. So it's a prize that is based on scientific work but has led to some globally accessible, commercially viable innovations. And globally accessible also means that they should be available to any people, be they from rich countries or poor countries, or whether irrespective of their own social standing or financial strength. So we have two selection committees, one pre-selection committee that goes through the kind of the bulk of the proposals and then gives a short list to the International Selection Committee, who will complete its work in June next year. And then the board of the Technology Academy Finland will make the final decision, and the awarding ceremony will be in November 24. So, as I said, the nomination portal is open on the 1st of April, and there's 7 months' time to submit nominations. So I hope that you will take this message back home to your peers and your institutes. Thank you very much.
Thank you, Dr. Elila. The small group sessions will be starting at about 3:40, so we do have time to take a couple of questions if anyone has any. Otherwise, you're welcome to stay back and have a chat, or we can see you outside. I think, does anyone have any questions in the house? Okay, can I invite you to take your seat? I'm just going to make some housekeeping.
Okay, thank you.
Okay, so thanks for staying with us this afternoon. I have just a few more instructions for the 3 groups of people who have different programs this afternoon. We're just going to flash a slide quickly to show you that. The first group will be the people who signed up for only the tours. Do meet at the registration area at 4 o'clock. We'll take the attendance and the buses will be there. For those who are attending the small group sessions as well, please head on now to level 3 and then go down to the registration area at 4:30 for the tours. And for those of you who didn't sign up for either of that, we have buses going back to the hotels at 3:45, 4 and 4:45.